We will Hayson is a student of electrical and computer engineering from University of Nigeria, Israel, and he will present a paper that he wrote with his undergraduate final project. The work was done together with Terkovich and Professor Stanley Rossman and under collaboration of Ben-Gurion remote sensing robot.
So, hello everybody, my name is Ivan. First of all, I must say that it's a great honor for me to be here today. And also it's my first time I'm presenting, so I'm a little bit excited. I hope you will enjoy, and also I hope I will enjoy. So let's start. Today I'm going to present you the research that we have done about machine learning for detecting anomalies in SAR temporal data. This is a short outline for today's talk, and I will start with a small introduction about what we're talking about. Then I will talk what data we used. I will present our suggested algorithm. I will show some results, and I will explain how we validated those results. And finally, I will talk about our conclusions, and hopefully, if we have enough time for questions, I will be happy to answer. So, our research is in the fields of anomaly detection in remote sensing data, especially talking about multidimensional data. In such data, not just the spatial domain is considered, but also another domain may be considered, such as spectral domain if we are talking about hyperspectral data, or time domain if we are talking about temporal data. Because we are dealing with anomalies, so one may ask what will be defined as an anomaly. So defining an anomaly can be a very complex job. The common assumption is that anomaly will differ from its surrounding pixels due to its dissimilar signature. It can be a different spectral signature or different time signature. Some of the difficulties that we are dealing with is the first one, we will need to define what are the normal clusters in data. And as we know from many other problems, that this can also be very hard. Second, we will need to choose a proper threshold for our algorithm that will be appropriated for the data and the application that we are using. So our research will be mainly focused about SAR, synthetic aperture radar, SAR temporal data. As for our final goal, we want to develop an algorithm for anomaly detection that will use data adaptive thresholds and also dimensionality reduced. In order to achieve our final goal, we initially wanted to see first if we can apply a machine learning method called NMF to SAR temporal data, which I will elaborate on later. And second, we want to see if we can apply to SAR temporal data other anomaly detection methods that we know work fine for other multidimensional data. So as I said, we mainly focused about SAR temporal data. Our data is presented as a 3D cube, where each layer in the cube is the same spatial region, but the image that was taken in a different time. It means that if we take a single pixel, it will be a vector, where each coordinate of that vector is the same region but in different times. In our research, we used just the intensity values of the SAR data, therefore it might have a high spectral noise. There is some more information about the data that we used. It was of Palmachim region here in Israel. It was taken by the TerraSAR-X project. Each image contains roughly 4.7 million pixels. We have 24 images that was taken between 2011 to 2012. Each image, the difference between the images is about 2 to 3 weeks. Therefore, the number of layers in our cube, capital L, is 24, and the total number of pixels, which is noted by capital N, is roughly 4.7 million pixels. So in our research, we decided to use a very well-known machine learning method. It's called non-negative matrix factorization, or briefly NNMF. You can look for it. There is a lot of papers about it. The main idea is that for a given dataset A, which can be represented as a matrix of n data points from an L-dimensional space, we want to reduce the data dimension and and also to extract trends from the data. The dimension reduction is done by extracting k features from the data, where k, which is the choose of the user, needs to be much smaller than the initial number of layers L. Later we span our data using those k trends. So let's take a look how we get the composition. So we need to solve this minimization problem. We are looking for two matrices, W, which is the feature matrix or a basis matrix of k n members, and H is the coefficient matrix. We also call it the hidden variables of the data, where each column of H is corresponding to a column vector in the original data. We also restrict our search for matrices which all their elements are non-negative. By that, we are not allowing any subtractive combination of the n members. And there are also some more variations of the NMF. One of them is called sparse NMF, which is basically the same, but we add another term. This one is this term enforces more sparseness over the columns of H. The reason we did this because we want to span our data using as less n members as possible to describe each pixel in the data. So we choose to base our algorithm over a well-known anomaly detector that's used for multidimensional data. It's called RX detector. We can see from the formula here that for a given pixel x, we want to calculate a distance of that pixel from the data distribution. Mu represents the mean background vector, which is taken over the time dimension, and sigma is the covariance matrix, which are both estimated from the data. Basically, the RX detector computes for each pixel its analogous distance from the data distribution. The RX detector has also some variations. Two popular ones are, the first one is the global RX, in which the mean background vector is computed using all the pixels in the data. This will refer to big anomalies that will be probably of the size that is bigger than 1 pixel. The second one is the local RX, which uses local estimation for the mean background vector using the 8 neighbors of the tested pixel. This will refer to small anomalies of the size of pixel or maybe sub-pixel anomalies. Okay, so this is a short overview of our algorithm. We first get our input SAR data queue with the L layers. First, we apply a pre-processing stage where we first use log normalization. We apply the log function over our dataset in order to avoid high saturation due to the speckle noise. Then we convert the data from a cube into a matrix, where we take each layer, which is an image, and we vectorize it into a row in the matrix form representation. The matrix form will be noted by a capital A. Then, in the main part, we first look for a value of k, which is the reduced dimension. We apply the NMF over the matrix A using the selected k. Then we apply the RX anomaly detector over the reduced data. The reduced data, I remind you, represented by the matrix H, which is the coefficient of the hidden variables of the data. And also we apply the RX over the old data. Then we apply some thresholding method, and we decide which pixel will be considered as an anomaly and which pixel will be considered as normal. So now I will explain you how we choose the value of the reduced dimension k. So as I said before, the value of k needs to be much smaller than L, otherwise we didn't reduce the dimension. Therefore, we want to understand how many different trends there are in the data. For that, we use the k-means algorithm, which for different values of k. The k-means algorithm extracts centers. In that case, it will be trends from the data. For each iteration, we calculated a loss function that is composed from two criteria. The first one is the distance criterion, which computes the total sum of distances of each pixel from its corresponding center, or more precisely from its corresponding trend. As we increase the value of k, this criterion should be reduced due to overfitting. Basically, if we will have as an input for the k-means a large value of k, we will fit for each pixel its own center, so basically it will be not useful. So the main idea of this criterion is to understand what is the density of the trends in our data. The second criterion is the correlation one, which you are seeing here, which checks the measure of correlation between the resulted trends. For this criterion, we want as less correlated centers as possible, otherwise we will use duplicate trends to span our data. So what we did, we applied the k-means algorithm for different values of k, and in each iteration we take the k centers, we compute the correlation of all all centers, we put it in a matrix M, and we check using the Frobenius norm how much it goes to the identity matrix. So basically, as you can see, there is a trade-off between the two criterions. While increasing k, the first criterion should be reduced, and as for the second criterion, while we increase k, the error will be increased, the correlation error will be increased, because we raise the probability to get another center that will be correlated with a center that we already got. So after that, we take the average of the two criterions and we find the minimum point of the function. The argument will be our wanted k. For our data, it was k equals to 4. So now, as I said, we applied the NMF method. What you're looking at is actually the matrix W. Those are the trends that we extracted from the data, the four trends. Each trend has its own time signature, and we can see that they are very different from each other. So using those four trends, we will span all our data using the coefficient matrix H. So here we can see some images of the original data at different times. We can notice that it will be very hard to track changes between each image. From the other end, in the second row, we can see the reduced data H. Each image represents a row in the matrix H. So as I explained before, we can present each vector in the original data using the matrix W multiplied by a column vector from the matrix H. So basically what you're looking at in the second row is actually the hidden variables, or how each trend affected a specific region in the data. So if we use the matrix H, we can identify changes in the data more easily, and also to classify the trends in the data. Here is another look. If you will take a close look in this region, in the marked area, you can see that those pixels are much brighter compared to the same region in the other entries of H. So if you will take a specific pixel in that region, and we will remind the matrix multiplication rules, because the value of that specific pixel in the other images is very low, that means that we can present a specific pixel here using only one end member. In that case, it will be the second trend, W2, and this is true due to the fact that the NMF is not allowing us any subtractive combination. Therefore, we can neither use a specific trend or neither not use it at all. Okay, so this is again the overview of our algorithm. Now, after we got the result of the reduced data, we apply the RX detector both on the reduced data H and over the old data A. And now I will explain you how we choose our thresholds. So we presented each pixel in the score plane of the RX detector results. What you're looking at is the y-axis are the results of the RX detector applied on the reduced data, And in the x-axis, we are seeing the results of the Rx applied on the reduced data. Then we decided to divide the data into two groups. The yellow one, which we name it the main cluster. Those are pixels that got I and similar scores both on H, the reduced data, and on the old data A. So we assume that a pixel that contains a valid anomaly will remain with the same score before and after the dimensional reduction. We also choose another cluster, which is the red one. We call it the subcluster. Those pixels got low scores on the reduced data H and high scores on the old data. This group may contain valid anomalies that was missed after the dimensional reduction. So basically, we decided to declare a pixel to be an anomaly if it contains in one of those two groups. The reason we decided to take the subcluster group is in order to compensate on those anomalies that we may lost due to the dimensional reduction. So now I will show you some results. In figure A, we are seeing the anomalies marked on the SAR data. This is, we take just one representative of the SAR data cube. So here we are seeing the yellow cluster, here we are seeing the red cluster. So because we didn't have any labels for our data, we decided to validate our results using the Google Earth. Because Google Earth has high resolution images, and also, which is the most important, has different images from different times of the same region. So with that, we could validate our results. So this is a Google Earth image with the places that we found. This is the yellow cluster, this is the red cluster. So now I will explain you what we are seeing. So the red cluster is sludge pores of the Tel Aviv region wastewater treatment plant. For those of you who don't know, sludge is a product of the wastewater treatment process, which being removed from the containing pores in a periodic procedure. Therefore, it was targeted as an anomaly. So basically, you are seeing here the different pores. If we take another look on the last image, we are seeing that our algorithm could detect each of the pores. As for the second one, the yellow cluster, this is a place where a new commercial center was under construction on the same dates that our data was captured. Okay, so this is another small experiment that we did. We increased the size of the main cluster to contain more potential anomalies, as you are seeing here. We see that the results are geographic segmentation of the data. That means that although we add more pixels, we are seeing that most of the pixels are not just noise or just meaningless points. We are seeing that it got some roads, some commercial centers, some industrial facilities, the borders of a lake there is in this region, and there's even a small military base here. So basically what we are seeing is kind of geographic segmentation of the data. So for conclusion, we have seen that the NNMF allows us to find trends from SAR temporal data. Those trends are time signatures that represent the changes in the data. Also, anomaly detection on SAR temporal data allows us to find unusual changes in the data, or in otherwise we call it anomalous change detection. Also, we saw that by comparing the results of the RX detector with and without the NNMF, we succeeded to classify the anomalies. We've seen that we got two different groups which describe two different types of anomalies. So, as I said before, this is an initial work for developing anomaly detection techniques on SAR temporal data that involve machine learning methods. For this stage, we are satisfied with the results, but we know there is a lot of more work to be done. So thank you very much, guys.
Thank you very much for your presentation. Your question, please.
Yeah, I'm trying to understand what you mean by an anomaly. Like with weather conditions, would that produce anomalies?
Well, that's a good question because specific what you are looking at is the SAR data. SAR is not so much affected due to weather conditions because this is one of the good properties of that radar. So in that case, it won't affect the results.
So is it activity on the ground that?
What we got? Yes.
Is that the main?
Yes. For example, I can give you a good application for that. For those of you who don't know, in Israel we have some problems in our south border with some tunnels. So it's very deep. It will be very hard to detect the tunnels. But one way to detect it is using SAR imaging. And if we check the difference, so if we are using, we may use this type of algorithm, and we can track changes of the surface height due to the high resolution of the SAR radar. So by detecting those changes, we might, because if someone is digging under the ground, the surface may go down a little bit. So this is a good application.
More questions? Very careful. One question.
Yeah.
Could you comment on the requirement of data? You say you have 24 data sets.
Mm-hmm.
If you just had in January 2011 and December 2012 two data sets, what would that do together?
Sorry, I didn't.
So say you're trying to map the change in geography.
Yeah.
How important is it to have? Could you just have one data set from 2010 in January and one data set from December in 2012?
So of course, okay. So first of all, I must say that we started to implement this type of algorithm on other data sets. For example, on hyperspectral data, we used the same idea and it showed also good results. For your question, of course, as we have more data, it will be more useful. I don't really know, but I think it may track changes. Of course, if we will have more data, the changes will be more interested.
So are you looking for?
Yes.
So are you looking for smaller changes, or if you get a big change in two data sets?
Yes. Well, if we will get a big change, we will get it. Probably we will get it. The idea is to track those changes that other change detection algorithms will. It will be hard to track those changes with them. So we are looking for more small changes in the data and not for the big one.